tackling now questions 4M4 through 4M6 of the second edition of Statistical Rethinking. 4M4 is going to ask us to build a model predicting student height over 3 years. And it's going to ask us to defend the priors that we choose for that model. So we'll get into that. And questions 4M5 and 4M6 ask us questions that want us to reflect about our prior distributions that we select for our model, and to try to refine the model accordingly. And so we're just going to do these steps as we build the model. Okay, so again, we want to build a model, a regression model of height in students for over 3 years, where each student is being measured each year, presumably. So starting with the model, so we're trying to model height, and we're modeling it as a normal distribution with mean mu and standard deviation sigma. And then you'll also notice the subscripts, where S I'm using to stand for a particular student, right? So each student will have its own number, right? And so the 57th student, S will equal 57 for the 57th student, say. And Y for year is denoting one of the 3 measurements that is taken on a student. Okay. So the average height, mu, I'm modeling with this linear model here. Okay. So let's look here at this little parenthetical term. So where I'm taking the year that a particular measurement is being made, and subtracting off the average year or mean year, or 1.5. And all that does is when the measurement is before 1.5, then this parenthetical term is negative. When it's at 1.5, it would be 0. And when this term is greater than 1.5, 1 plus 2, that's 3, that's 6, divided by 3 is 2. So it's not 1.5, sorry, it's 2, right? So at 2 years, that value will be 0. And then above 2 years, it'll be a positive number. And then below 2 years, or at the 1 year measurement, it will be negative. Okay. And beta here is how much the student is growing each year. All right. So at year 2, this term will be 0, which means the entire term will be 0, which means that the average height for year 2 will just be alpha. And it says that alpha is a normal distribution with a mean of 65 inches and a standard deviation of 5 inches. Now, as we take measurements after year 2 or before year 2, right? So if it's after year 2, then this number will be positive, which means that the student will have grown by beta at year 3. Or if it's at year 1, they will not have shrunk, because I'm also going backwards in time, but 1 year prior, they will be beta inches shorter. Okay, and so beta is the growth rate here. And so for beta, I'm using a half normal distribution of mean 1 and standard deviation 1. And so what a half normal distribution does is it only allows positive values, right? And that is reflecting the idea that we have that's shown here in question 4 and 5, that the students are only getting taller. They're not shrinking from year to year. So by using a positive growth rate, or a necessarily positive growth rate, I'm trying to make sure that I'm not allowing my model to assume that students are shrinking. Okay? And then finally, for the standard deviation of height, I'm using a uniform distribution that has a minimum value of 0 and a maximum value of square root of 25.2. How do I come to that? It's because question 4M6 tells us that the variance is never more than 64 centimeters. But I, again, am stupidly using inches, and that converts to about 25.2 inches. And my model is using not variance, which is what this tells us, but standard deviation, right? So standard deviation is the square root of variance. Therefore, you get the square root of 25.2. Okay. I think I've explained everything important in my model here. And now we need to go through and defend our choice of priors. And so what this means is we need to make sure that our model is expecting to see data that it is likely to see, right? So in other words, if based on my prior distributions, my model is not expecting to see what would be very expectable heights of the students, it's going to skew the posterior distribution, right? Because it will not be expecting to see those particular heights. And so it will assign them in the prior distribution a low probability of seeing those heights. And even when I see those heights, it's going to kind of downplay the impact of those completely reasonable heights. And we don't want that. We want our model to expect to see what it's going to see. And so right now we have these prior distributions, right? We just have two prior distributions, but those somehow combine to give us a prior for mu as well as for height. And so we need to simulate what the model expects to see for height. Okay. So we're going to do that. So here's the code for it, and let's break down the code. So we're going to simulate 100 students, but you could do however many you wanted. And I'm just going to put in my prior distributions that the model actually contains, right? So I have a prior for alpha, right? Prior for alpha is normal, 65.5. Okay, that's what we have here. Then I have my growth rate beta. It's a half normal distribution, 1, so I have my normal distribution, and I'm taking the absolute value of that to again make sure that I'm not allowing students to shrink over time. So also notice that I'm using the R norm functions here and the R uniform because I'm randomly generating samples here. Okay, and then for my standard deviation for sigma, I'm using again a uniform distribution between 0 and square root of 25.2. Okay. Okay. So now my model uses these terms year. Okay. And so I need to define those here in my model. And now I need to actually generate some values for height. And so what I'm going to do is I'm going to build a matrix that will start out with no data, but it's going to have one row for each student that I'm simulating. So it's going to have n rows, which is 100. And I'm going to have 3 columns. Why 3 columns? Because I'm taking 3 measurements, 1 over each year. Okay. And so, like I said, this matrix starts out empty, and then I'm going to fill it in with this for loop. And so I have, so for each student, or in other words, for each row, and for each year or each column, and so now I've specified a student and a year, I've specified a row and a column, so I've specified a single cell in this matrix. Okay. I am going to assign a value to height for this particular cell. What cell? Student by year, row by column. Okay. And what is that value in that cell going to be? Well, it's going to be a value that's taken from a normal distribution. Okay. So I'm going to put one value in that cell, in this cell, from a normal distribution that has a mean of, well, this is just my linear model from above. Okay. So I'm going to take a value from A, which I defined here, a value from B that I've defined here, and multiply it by the year 1, 2, or 3. Okay. And then the standard deviation of this randomly generated value is going to be one of the values that I generate from here. Okay. And now, after that matrix gets filled out, rather than looking at all of the numbers, we're just going to plot it. Okay. So let's run this code. All right. So here's what our numbers look like. Okay. So along the x-axis we have the year 1, 2, 3. Right. We don't have measurements at 1.5 and 2.5. And the height in inches. So our model is predicting things somewhere around 50 to 85, and so that's a reasonably wide range, and it doesn't seem to exclude any probable values. And the bulk of it is around 55 to 70 inches, and to me that seems like a reasonable prior assumption. Now, most of these values are going, it's a little bit hard to see, but most of these lines, let's just put 10 in there, most of the lines have kind of an upward trajectory. And well, that was kind of a bad sample, but there's quite a few that have this downward bend. But the reason that many of them, or the reason that they are going up, is again a function of the fact that we have this here, the absolute value of we're using the half normal distribution for the growth rate. But why are some of them going down? We took this step to ensure that they're going up, that they're growing. Well, the reason that some of them go down is because the standard deviation is allowing them to go down. And so something that we may be able to do is to somehow tighten up the standard deviation, but we're just kind of going by with what the question was allowing us. So these trajectories here, these growth trajectories, maybe they actually happen, and so maybe it's good that we have those in the model or allow for them to be in the model. But in this case, we're going to ignore it, and we're going to trust that our data will correct these weird downward deflections in the prior, that the data will correct those so that the posterior will not have these shrinking trajectories. Okay, that's all.